The main theorem is going to be called the monotone convergence theorem. So this is one of the, within sequences, the study of sequences, this is like the big thing. Okay? We'll discuss the theorem, we'll show you how to apply it, how it's useful, and talk about a few examples. Okay. All right, a few definitions first. The definition involving a bounded sequence, well, I guess it involves two things, really. We can bound a sequence in two ways, from above and from below. So we say that a sequence is bounded from above if there's some number, big M, that the sequence is always less than or equal to. The value of the sequence is less than or equal to. Okay, and we call such a bound an upper bound. We can also talk about a sequence being bounded from below, where we just reverse the inequality sign. Okay? And we will refer to little m as a lower bound. Now, if we have the situation where a sequence is bounded from above and below, then we call it a bounded sequence. So let me show you some examples to really give you an idea of what's going on here. So just look at these three basic pictures here. You can see for this particular sequence, the sequence looks like it's bounded below by positive 1. Okay? But the sequence wouldn't be bounded above. In this graph, the sequence is bounded above by positive 1 and below by 0. So this middle sequence is a bounded sequence because it's bounded above by some number and below by some number. This sequence also is bounded above and below. Okay, so there's some examples of some bounded sequences. Let's just, think about some sequence, say sin n. We know that sine's bounded here, so that the upper bound would be positive 1 and the lower bound would be negative 1. Okay, now some sequences aren't bounded at all. They don't have an upper bound or a lower bound. So for something that's not bounded, either above or below, think of something like this. Instead of sin n, what about n sin n? Okay, that sequence is neither bounded above nor below. Now these values, at least for this sin n, I've just chosen big M to be 1 and little m to be minus 1. I could choose other values like big M equals 2, big M equals 100, little m equals minus pi. They're still correct, okay? They're still bounds on the sequence. So there is a number, not necessarily a unique value. Okay, an important theorem, convergent sequences are bounded. That is, if we have a convergent sequence, then that sequence must be bounded. Okay, conversely, if you have an unbounded sequence, okay, from a practical point of view, if you have an unbounded sequence, then it can't converge. Okay, that's probably of more practical use. And this is the main theorem here. Okay, I think in your notes I've removed one picture because I thought it was slightly unclear, but it should be okay. The monotone convergence theorem. The MCT. Now, when I talk about an increasing or a decreasing sequence, it's kind of like an increasing or a decreasing function. Okay, you can think of, you're either heading up as you move along the sequence or heading down. So what does this monotone convergence theorem say? If we have an increasing sequence that's bounded above, then the sequence must converge. And secondly, if a sequence is decreasing and bounded below, then the sequence converges. Okay, now these theorems it's slightly abstract, the monotone convergence theorem, because it doesn't tell you what the limit is. Okay, it just tells you that the limit exists, and in the first case, the limit is less than or equal to this upper bound, and in the second case, the limit is greater than or equal to the lower bound, or a lower bound. Okay, it's very powerful. It's something that you can use all the time, just to show that a limit actually does exist. Okay? Now, I'm not going to prove it, but we are going to look at how we can apply it. Okay? But before we do that, let's have a look at geometrically what's going on. Suppose I've got a sequence. Here it's just plotted in the plane. And big M is any upper bound for the sequence. What you can see from the picture, the sequence is increasing and it's bounded by this number, big M. What the monotone convergence theorem says is that the limit of that sequence does exist, and the limit is less than or equal to whatever that number, big M is. Okay, so you can see in this case, the limit is actually less than big M. Okay? So it's like a graphical representation of what the monotone convergence theorem says. Okay, so it's a very powerful theorem, and it's something that you'll use quite a lot in this course. Now, it does have limitations. It's very general, but it does have limitations in the sense that it doesn't tell you, at least in the form that I presented, what the limit actually is. Or you know that it's less than or equal to your bound on the sequence. Okay? Now, let's have a look at an example. Say this sequence here. Now, this sequence is an increasing sequence. Okay? Now, you can also easily bound this. Let's say, it's for n greater than 0. You can easily find an upper bound for this particular sequence. Anyone? 1? 1's a good choice. But you can also have an upper bound of 2, 3, 100, 64. Okay? They're all correct. They are all bounds, for upper bounds, for that sequence. But think of all the upper bounds for this sequence. What's the smallest one? Positive 1. Okay? Now, this converges to 1 in the limit, right? Let's just go to 0. Now, the 1 is a special bound. Of all the upper bounds, 1 is the least, the lowest upper bound. Okay? So, although I haven't explicitly stated it, the monotone convergence theorem does give you a little bit of constructive information. If you have, say, an increasing sequence that's bounded above, the limit does exist, and the limit is so-called least upper bound. Okay? So of all the upper bounds, it will converge to the least upper bound. Okay? Okay? So to put this into some sort of practical context, let's go back to I'll put this up in a minute. Let's go back to this picture. Let's think about 1 on n. Okay, the sequence 1 on n. That is a decreasing sequence that is bounded below by lots of numbers. Minus 100, minus 10, minus 5, minus 4, minus 3. All the way up to 0. 0 is the greatest of all the lower bounds. And you can see that, of course, 1 on n converges to 0. It converges to its greatest lower bound. Okay, now this sequence here is neither increasing nor decreasing. Okay, so you can see that it doesn't converge to either its greatest lower bound or its least upper bound. Converges to something in the middle, right? So the monotone convergence theorem is really tied with bounded and monotonic sequences. Okay, so this is important. This is something that you can use. Let me show you another application of the monotone convergence theorem. So I don't have this written down, but this is actually one of your tutorial problems. Okay, so you might just, if you've got a bit of extra space down here, you might want to sort of see if you can fit it in here. Now, I can define a sequence in the following way, a so-called recursion relation. Yeah. Okay, so this is kind of like what we refer to as a recursively defined sequence. You start with some value of the sequence, a sub 1, in this case it's 1, and then to generate a sub 2, you use this over here. So you'll put 1 into here, and a sub 2 would be root 2. Okay, then to get a sub 3, you would put a sub 2 back into here and work that out. Now, this particular question asks you to show that the limit exists and calculate the limit of a sub n. Okay? So that's what we're going to do. We're going to use the monotone convergence theorem to do it. Okay, so essentially, all we need to do is tick off the two conditions of the monotone convergence theorem. We want to show that the sequence is monotonic. It's either increasing or decreasing. And it's bounded, either above or below, depending on what, whether it's increasing or decreasing. If we can tick off those two claims, then we know the limit must exist. And then after that, it gives us a little bit of a hunting license. Maybe we can go and hunt for the limit. Okay? Okay, so how would we do this? Well, sometimes you can play with this and look at the ratio of a sub n plus 1 over a sub n and show that's either strictly greater than 1 or strictly less than 1. But this one isn't so easy. So what we're going to do is use induction. Okay, so let's have a look. A sub 2, that is root 1 plus 1, root 2. Okay, root 2 is greater than 1, which is A sub 1. So it's true for this first case. So we assume A sub k plus 1. Oh, actually, let's use that. A sub k is greater than A sub k minus 1. Okay, so what we would like to do then is show that this is true. A sub k plus 1 is greater than A sub k. So let's consider this. Now, A sub k is, by assumption, is greater than A sub k minus 1. And what is this? Well, that's just, by definition, A sub k. So I've got my inequality. A sub k plus 1 is strictly greater than A sub k. So by induction, then, this must be true for every n So, yep, my sequence really is increasing. Okay, so that's one half of the conditions of my monotone convergence theorem. I've shown that it's monotonic. Now, if it's increasing, what I would like to do is show there's an upper bound for every A sub n. Okay? Now, it can be tricky choosing the upper bound here. And sometimes you have a bit of a hint. I'm going to make the following claim. A sub n is bounded above by positive 3. Now, you don't need to have positive 3 here. Just positive 3 works well. Okay? You'll see why in a minute. Okay, you could have any sufficiently large number there. Okay, so again, let's do it by induction. A sub 1 is 1. That's certainly less than or equal to 3, isn't it? Yes. So let's assume it's true for some k, strictly greater than 1. A sub k plus 1, well, by definition, it's just that with n replaced by k. And by our assumption, A sub k is less than or equal to 3, so it'll be less than or equal to root 4, which is just 2. Now, is that less than or equal to 3? Yes, it is. Nice. Okay, you can see how the choice of 3 there was quite, if you wanted to work out simply, a good choice is kind of required there. So what does it mean? Well, it means by induction, A sub n is bounded above by 3. So, okay, our two conditions of our monotonic convergence theorem are now satisfied. We definitely know the sequence, recursively defined by star, is increasing, and it's definitely bounded above by positive 3. So, what does it mean? It means that the sequence defined through star must have a limit. So by the monotone convergence theorem, there is a number, say L, which is less than or equal to 3, such that A sub n converges to L. Now, the next question, of course, is, Well, how do I calculate L? What is the limit? And some of you may already know how to do this. Any ideas? Any ideas? How might I calculate the limit? Okay, I know it's less than or equal to 3, but anyone, any ideas? Any ideas? Guess? Well, essentially it comes from here, okay? Having the subscript n plus 1 doesn't really change anything, right? If a sequence has a limit, a sequence can only have, if the limit exists, right, it's unique. A convergent sequence only has one limit. So, what does it mean? Well, if I take the limit over here, I'll get L. And if I take the limit over here, I'll get root 1 plus L. Maybe I can solve that equation for L. Okay? So let's calculate L from star. Okay, so essentially all I'm going to do is, if I take limits everywhere, this will go to L, this will go to L, and I'll end up with L equals root 1 plus L. Now, that's not quite so easy to work with, so what I'm going to do is just square both sides. Okay, so that'll be L, that'll be L. I'll actually, when I rearrange it, I'll get that. Okay? Now, you may be a little bit worried here because by squaring it, I've actually introduced two values of L there. Yeah. So, as long as we're careful when we solve this quadratic equation, you know, we're going to get two values of L there, but we only want to select the one that we really want. Okay? So, you can solve that a variety of ways. I think I just completed the square, and you'll get something like this. Is that right? Root 5. Okay, so which one do we want? One of these is going to be positive, one of these is going to be negative. Well, we want the positive value for L, because obviously the values of our sequence have got to be positive. So the limit will be this. Okay, now, some of you may be looking at this and going, hang on, Chris, why didn't I just start there, assume the limit exists, and then go to that thing straight away? Well, you could do that. It's dangerous, though, because you don't know whether the limit exists or not. Okay? You don't know whether the limit exists or not. So, you know, you're sort of scratching around there, hoping something happens. That's a good question. Okay, one of your tutorial problems. So that's one sort of pseudo application, but the following is slightly more definite. It's known as the method of successive approximations. And in fact, I use this method in my own research from time to time.
Page 20 you've got quickly, but you said you're going to put it back up later.
Oh, yeah. Yep. I've only got 2 slides to go. Now, You may have heard of mathematicians by the name of Picard and Louisville. Okay, French mathematicians. Very powerful. I love reading some of their work. Now, they introduced a sequential way of approximating solutions of equations. So suppose we have an equation of this kind where f is some continuous function. Okay? This kind of problem is known as a fixed point problem. Okay, so any x satisfying equation 1 is called a fixed point of the operator f. Now, if f is continuous, the method is as follows. You start with some value, a sub naught, and then you define a recursive representation for your sequence a sub n through the f here. Okay? Now, if f is continuous, then and the a sub n converges to some limit, a star, then actually, if you take limits here and here, you get a star equals f of a star. So that means that a star, the limit, will be a fixed point of f, or a solution to the equation 1. Okay? Now that may not seem like much, but that method has been used over and over and over and over again. Okay? It seems pretty simple, but it's really effective. Okay? So in one sense, this method can be related in the following way. Suppose this is a very abstract equation, and I want to know, is there an x that satisfies this equation 1? Does f have a fixed point? This so-called existence theory, does a x exist satisfying x equals f of x? This existence theory is then broken down to, does the limit of that sequence exist? If the limit of a sequence exists, equation 1 will have at least one solution. Okay? Anyway, he's a bit of a hero of mine.